All right, let's look at where this trig stuff really comes from, because trigonometry's been around before we even had a coordinate plane. So, we never used points but we still had trigonometry. So really it comes from right triangles. Okay, it's actually called right triangle trigonometry. So for those of you that had me last year, you should remember this SOHCAHTOA. Okay, remember. So this simple phrase tells you everything you need to know about right triangle trigonometry. So SOHCAHTOA, so the sine equals the opposite over the hypotenuse. Okay, ka, that's the cosine, and this equals the adjacent side over the hypotenuse. The tangent equals the opposite side over the adjacent side. Okay, so this should make sense when we look at our unit circle and think about what we had before. Okay, because what we were saying is that the sine of some angle, if this is our angle, the sine equaled the y value, because sine is opposite over hypotenuse. In the case of our unit circle, the opposite side would be y, and our hypotenuse is 1. So that's why the sine on our unit circle was always just the y value. Okay. Another way to think about this is sine is the reciprocal of the cosecant. So I could just say that this is 1 over the cosecant of theta. So if I know the cosecant, if I reciprocate it, I get the sine. But this opposite over hypotenuse, that's going to help us out when we get to dealing with things that aren't on the unit circle. Okay, because if we have just a right triangle and we want to use trigonometry on it, our hypotenuse is not necessarily going to be 1. Okay, maybe I have a 3, 4, 5 triangle. Okay, and then I'm going to want to use 5 in place of the hypotenuse, and I'm not going to have a 1. So it's not always just going to be y, because sometimes we're not on the unit circle. Okay, so cosine, okay, we said was the adjacent side over the hypotenuse of our right triangle. Remember, hypotenuse is always the side that's across from the right angle. And this should make sense because on our unit circle, the adjacent side of the angle, so the side that touches it, is our x value. And again, our hypotenuse is 1. So that's why this was just x. The tangent is opposite over adjacent. So opposite was y, adjacent is x. Okay, so that's why this was y over x. So cosecant is going to be hypotenuse over opposite. It's going to be, secant would be hypotenuse over adjacent, and cotangent would be adjacent over hypotenuse. But if you're dealing with opposite, adjacent, and hypotenuse, you're probably not going to have to use these at all. Okay, so these are mainly used for the unit circle type calculations. Okay, but they are reciprocals, so let's put the reciprocals in here. So cosine is the same as 1 over the secant. Tangent is the same as 1 over the cotangent. Cosecant is 1 over sine. Secant is 1 over cosine. And cotangent is, let's think of it this way. Since tangent is sine over cosine, cotangent would be cosine over sine. Sometimes when we're simplifying complex trig functions or expressions, we're going to want to change everything into just sine and cosine to see if we can get things to cancel out and work out a little better. There's some Pythagorean identities also. If you look, I've got a right triangle, so I can use the Pythagorean theorem. And so I would take this side, which is x squared plus y squared would equal 1 squared. Well, x is the same as saying cosine in our unit circle. So if I square the cosine, add it to the sine squared, I should get 1. And really this works even if your hypotenuse is not 1, because let's say we had a hypotenuse of something else, if it was 5, 5, 5, all those are going to end up canceling out. So if you're on the unit circle, it'll work. So this just comes from Pythagorean theorem, so that's why it's a Pythagorean identity. If we divide everything by cosine squared, I get a new Pythagorean identity. So sine squared over cosine squared, sine over cosine is tangent. So sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And 1 over cosine is secant, so 1 over cosine squared is secant squared. This is another Pythagorean identity. If instead of cosine squared I divide everything by sine squared, now I'm going to get 1 plus, this is going to be cotangent squared equals cosecant squared. Okay, and these could be shifted around a little bit. So I could have secant squared minus 1 if I subtract the 1 over. So if you see tangent squared, you could turn it into secant squared minus 1. Again, I could subtract the 1 over here, and so if you see cotangent squared, you could turn that into cosecant squared minus 1. So the thing that's going to tip you off to these is anytime you see a trig function that's squared. Okay, there's probably some some Pythagorean identity you can switch it to. So here's some examples of things we can do with our trig identities. Let's see if I can move these around here. Okay. I'll put that one up in here. All right, so if we just use our basic trig identities, so knowing that tangent is sine over cosine, cosecant is 1 over sine, secant is 1 over cosine, things like that, we can hopefully simplify these. So cosecant, right, I know that that is 1 over the sine, and I'm multiplying that by tangent, which is sine over cosine. And when I switch things to this, I can see that I can cancel a sine out. And this would be 1 over cosine, which is, of course, secant. Okay, and this is a lot nicer than having two trig functions in there. So here we can do something also. Cotangent is cosine over sine. Of course, sine is still sine, but now I can see that I can cancel this out. So this really equals cosine of theta, which is a lot better than having two things there. A lot of the same things that we do with everything else we're going to do here. So if you see something like this, you're going to do what you usually do, which is distribute. So we're going to take this times that. So I get cosecant squared. Just a note about this. You can put the squared on there, or you can put it outside the whole thing. These are the same thing. So any way that you want to write it, but most times you'll see it written like this. I'm squaring the cosecant. I'm taking that off theta. And then I'd have cosecant theta minus cotangent theta. So it'd be minus cosecant, cotangent. Then I have plus cosecant, cotangent. And then minus cotangent squared. These two are going to cancel because they're identical and one's positive, one's negative. So I've got cosecant squared minus cotangent squared. Let's look at our Pythagorean identities and see if we can do anything with this. So I see that cotangent squared is actually cosecant squared minus 1. So I'm going to turn it into that. Okay, if I distribute this, I'm going to have minus cosecant squared plus 1. And I'll see that this is actually going to cancel. So this whole thing actually just equals 1. So those are some examples of the things you can do with your trig identities. We can also solve right triangles using SOHCAHTOA. So if I want to find out this missing side here, I could use the Pythagorean theorem to find the missing side. If I don't have one of these, or maybe I have this, and actually, let's say I don't have a side, but I do have an angle. So let's say this is, I don't know, we'll make it one that we can actually use, make it pi over 4. And if I want to find out this side, okay, so that's my x, I can set up an equation and say, well, this angle here, I know it's opposite side, so I know O is 5. And I'm looking for A, the adjacent side. Well, OA, that's tangent. So I'm going to take the tangent of this angle, the tangent of pi over 4. And I know that that equals the opposite side divided by the adjacent side. So then I'm going to be able to solve this. So tangent of pi over 4 of my unit circle, that's here. Okay, and my x and y values are both square root of 2 over 2. So when I take y divided by x, I get 1. So tangent of pi over 4 is 1. That equals 5 over x. Multiply both sides by x, so I get x equals 5. Okay, we'll do some word problems. There's a 30-meter line that's used to tether a helium balloon. And because of a breeze, the line makes an angle of approximately 75 degrees of the ground. Right, so we're just going to draw a picture here. Here's the ground. Here's my line holding the balloon. Okay, and here's my balloon. And this is making a 75-degree angle. And I know that the line is 30 meters. What is the height of the balloon? I want to know what this is. Well, I've got this angle. I'm looking for O. And I have the hypotenuse, okay? Because, of course, there's a right angle. This is the hypotenuse. So H equals 30. So O and H, that's SO from SOHCAHTOA. So I'm going to use the sine. I'm going to take the sine of 75 degrees, and that should equal the opposite, which I don't know, divided by the hypotenuse, which is 30. So we're going to solve this just like anything else. We're going to get x alone by multiplying both sides by 30. So x equals 30 times the sine of 75. And here's where you can use your calculator. So we're just going to type this in. Make sure you're in degree mode. So it's under mode. If you're going to use radians, you want to be in radians. If you're in degrees, you want to make sure you're in degrees. If you want to keep it in one thing all the time, that just means you're going to have to be converting to whatever you set it at each time. So I think it's just quicker to switch over to degrees. So now I'm going to type in 30 times the sine of 75 degrees. 28.977777. So it's about 29 feet off the ground. It's 29 feet. Or meters, because I'm in meters. Okay, so 29 meters. So I got another one here. A tapered shaft has a diameter of 5 centimeters at the small end and is 15 centimeters long. The taper is 3 degrees. Find the diameter of the large end of the shaft. Alright, so tapered shaft, which I've drawn a picture of here, which means it's smaller at this end and wider at this end. And the small end has a diameter of 5 centimeters. And its total length is 15 centimeters. And this taper, okay, so if I put this in here, the taper is going up 3 degrees. And they want to know how wide this is. So I'd have another identical taper down here. Okay, this is also 3 degrees. I only have to solve it once, but it's nice to just remember that. Okay, I'd have this. So really, this space between the two triangles I'm making would still be the 5 centimeters. So I need to find out what this is and double it and add it to my 5 to find out what the diameter of this side is. So I know this side. Okay, I don't know the hypotenuse. Actually, I do. I do know the hypotenuse because the length of the tube tapered shaft. Yep. Diameter is 5 centimeters small end, and it's 15 centimeters long. So I'm assuming they're measuring along the hypotenuse. I don't know. That's the only way I would measure it. Unless they're setting it up against something. I guess this is open to interpretation, but just to mix things up, let's have it be, let's say they're setting this up against a ruler and measuring it, so that means that they're not measuring the hypotenuse, they're measuring this baseline here, so we'll say this is the 15. Okay. Well, that means I'm looking for the opposite side. I have the adjacent, and I have the angle. So I'm going to use OA, which is tangent. I'm going to take the tangent of 3 degrees and say that that equals whatever I'm missing divided by 15. Opposite over adjacent. So again, I can type this in. If I solve for x, I have 15 times the tangent of 3 degrees. 15 times tangent of 3 degrees. I get 0.786 centimeters. Okay. 0.786 centimeters. That's what this is. I've got 2 of those. Okay, so I've got an extra 1.5 centimeters. Add that onto the 5 centimeters I had. So I have about 6.572 centimeters at the wide end. Okay, so there's a couple applications of trigonometry that you can use.